Hey guys, this is going to be Chapter 15, Part 2, the significance of the equilibrium constant. Alright, so what that means is, what does the equilibrium constant tell us? And if we have K, the constant, if it is a big number, then that means that there's more product than there is reactant. Because remember, the K is calculated putting the products raised to their coefficients over the product of the reactants raised to their coefficients. So if it's a big number, that means we have tons of numerator and very little denominator, because that's what makes a big ratio, right? And if K is small, then that means that there's more reactant than product. Because if you have a little bitty number, like 4.1 times 10 to the negative 31, then that means that the numerator here is going to be very, very little, and the denominator is going to be very, very big in order to give us that small number. So one thing that I want to emphasize here is scientific notation. Remember that if you have 10 to the 19, you're multiplying this 1.9 by 10 19 times. So that decimal place is going to move to the right 19 times. So that is an extremely large number, right? And then down here at the bottom, we've got 4.1 times 10 to the negative 31. And remember, if you have a negative exponent, that means that that value is actually down in the denominator. So we're dividing 4.1 by 10 31 times. And so this is a very, very, very little number. There would be a decimal place and then 30 zeros and then 4 1. So that's a very, very tiny number. It's a long number, but it's still a very, very small number. And so if we look at the pictures here, this big K at the top is showing that we have mostly product here, right? Very, very little reactant. So there's one reactant, there's the H2, and here's the second reactant, the Br2, and then most of it exists as product. Whereas down here on the bottom reaction, the small k is showing that we have way more reactant and very little product actually formed. There's only two that show product, and everything else would be a reactant. Okay, so to summarize, when k is much, much less than 1, so it's a very small number, the reverse reaction is favored. So the reaction wants to go backward and produce more reactant. Okay, so it doesn't proceed very far. If you only put reactant in the reaction container, then you're only going to get a very, very little amount of product and a lot of reactant left over. If, on the other hand, K is much, much greater than 1, that means the forward reaction is favored. So it wants to go in the forward direction, and it proceeds virtually to completion. So you're going to get mostly product there. There's not going to be hardly any reactant left in the container. And if K is about equal to 1, then neither direction is favored, and you have significant amounts of both reactant and product present in equilibrium. So you're going to have a lot of product and you're going to have a lot of reactant, and neither is really going to overpower the other. All right, so K is only calculated with equilibrium concentrations, first of all. You need to remember that. Okay, you can't just calculate K anytime during the reaction. K has to be calculated once the concentration of the products and the reactants stop changing. So here's my initial concentrations for this reaction. If we start with H2 and I2, those are the reactants, at 0.5 molar, and we don't have any HI, then at equilibrium, what we find that we have is 0.11 H2, 0.11 I2, and 0.78. So this is experimental data. This is what they found during the experiment. And if you plug those values, because remember we're only using equilibrium values for K, so these initial values won't work, we get that the K is equal to 50 by plugging those numbers in. And then on a completely separate experiment, we didn't have any H2, we didn't have any I2 at the beginning. All we put into the reaction container is 0.5 molar HI. And what they found at equilibrium, where these were the concentrations of our substances, we plug those in and we get the exact same K, because that's what it is. So this is what happens anytime you have any combination of the reaction. It doesn't matter if you're starting out with reactant, or if you're starting out with product, or if you're starting out with all three, like in this third example, they started out with 0.5 molar of all three, and we ended up getting these values at equilibrium, and we got the same K. All right, here they have 1 molar H2, 0.5 molar I2, and they still get a ratio that gives us this K here. So it doesn't matter what you start with, you're going to end up at the same place. All right, so if we calculate the equilibrium constant for this reaction, first I'm going to write down my K expression. So K will be equal to H2 cubed times C2H2 divided by CH4 squared. And then I'm going to plug my values in. So H2 is 0.112, and I'm going to cube that. And then C2H2 is 0.0451, and I'm going to divide that by 0.0203 squared. Okay, when you put this in the calculator, you really have to watch out for PEMDAS and make sure that you're doing it correctly. So the first thing I'm going to do is I'm going to calculate what 0.112 cubed is, and I get 0.0014049. And then on the bottom, I'm going to square the 0.0203, and I get 4.1209 times 10 to the negative fourth. And then I'm going to multiply the top and then divide by the bottom, and I get 0.154. And remember, K is unitless. It doesn't have any units. All right, now if you put this in your calculator and you do not get this answer, then you're not putting it in your calculator correctly, and you need to make sure that you do it stepwise. If you can put it in your calculator without doing it in steps, that's fine, but I just want you to check to make sure that you can put it in correctly, because a lot of students, what they do is they'll say 0.112 cubed times 0.041451 divided by 0.0203 squared. And when they put that square in, they're not really just squaring this number, they're squaring everything because they're not putting it in the calculator right. So make sure that you're putting it in your calculator correctly. All right, calculate the equilibrium concentration of CO2 with the given concentrations found at equilibrium. So I'm going to plug everything in, and this time I'm given the K. So first down here, real small, I'm going to write my equilibrium expression. And then I'm going to plug in what I know, and so I know that my K is 2, and my CO2 is what I'm looking for, and I have CF4 and COF2. Okay, so I have 0.065025, that's 0.255 squared, so all I did was square that and plug my number back in. So now to get rid of, because I want to solve for the CO2, so I'm going to multiply both sides by 0.065. So I get 0.13005. And then I'm going to divide both sides by 0.118. And I get 1.102. So sig figs, it would be 1.10. All right, now down here at the bottom, we're going to do one more. So again, down here, I'm going to write my K is going to be equal to HI squared divided by H2 times I2, and then I'm going to plug everything in. So my K here is 70. I'm looking for HI. And then I'm going to plug in my 0.02 for both H2 and I2. So I'm going to multiply those two together. I get 4 times 10 to the negative fourth is 0.02 times 0.02, and then I'll multiply both sides by that. And I get 0.028. And then I have to take the square root. And so sig figs, there's only 2 of them because leading zeros don't count, and so that's 0.17. And that's it.